So we've seen one example of palladium catalyzed carbon-carbon bond forming reactions where alkyl halides react with alkenes in the presence of a palladium catalyst, a triphenyl phosphine or arsine, a tertiary amine. You usually only need about 1 mole% of your palladium catalyst to get this reaction to go, to form dienes with the elimination of HBr. And we made 4,6 decade diene using this, which is called the Heck reaction. Basically just eliminating the elements of HBr and forming a new CC bond between the two alkenes. A very powerful reaction for forming new carbon-carbon bonds in a way that ordinary organometallics like Grignard reagents can't do for alkynyl anions, nucleophilic alkyl substitution. There are 3 variants, actually there are more than 3, but there are 3 I want to talk about. This reaction that fall into the class of palladium catalyzed cross-coupling reactions that all use an alkenyl or an alkynyl or aryl bromide and another organometallic. One of these is the Suzuki reaction. Suzuki was one of the ones that shared the Nobel Prize with Heck for this work. And the Suzuki reaction involves an alkenyl halide reacting with a tin organometallic. Often tributyl tin. So we will take an alkyl halide like that and react it with tin organometallic. And the elements of tributyl tin bromide will be removed. Using our palladium 0 catalyst with ligands on it. Again, generating diene, making a new CC bond between 2 alkenes. The mechanism is significantly different from the Heck reaction, though, because it involves an organometallic compound on the other side. In addition to the Suzuki reaction, it involves alkenyl halides with organotin compounds. Sorry, that's the Stille reaction, not the Suzuki reaction. I'm getting my S's mixed up. All of these reactions are named after people who begin with S. That's the Stille reaction. The Suzuki reaction, Suzuki is the one that shared the Nobel Prize, uses an alkenyl or aryl halide and an alkyl or alkenyl or aryl will And unlike the others, it works on ordinary primary or secondary alkyl halides as well. So you could actually take just 2 iota butane and react it with an alkylboronic acid to eliminate the boron and the iodine to make an ordinary carbon-carbon bond. So you're essentially alkylating the end of an alkene. You couldn't do that with an alkenyl organometallic because you'd get nothing but E2 elimination. So again, we've got our new CC bond. This time between an sp2 and an sp3 hybridized carbon. Again, it involves a palladium 0 catalyst. And automatically triphenylphosphine or triphenyl RC. And the third palladium catalyzed cross-coupling reaction, which is useful because it reacts with alkynes. It's the Suzuki reaction. Which might start with an aryl iodide. In this case, iodobenzene. Plus an alkyne, and eliminate the elements of HI to form a substituted aromatic compound. And again, we have our new carbon-carbon bond. This time between sp2 hybridized carbon hybridized carbon. The Suzuki reaction involves the same palladium 0 catalyst, a copper 1 salt, cuprous iodide in this case, and a tertiary amine. Diisopropyl ethylamine, also known as Cumming's base. I'm going to illustrate the reaction for the Suzuki reaction, the mechanism for the Suzuki reaction, but the mechanism is very similar for the others. It's just a matter of what the other organometallic. This will involve an organocopper compound. This one will involve the boronic acid, and the Stilling reaction involves the organotin compound. But the tin, the boron, and the copper part of the mechanism are interchangeable. You might wonder where those boronic acids come from, or your entry into the Suzuki reaction. And it turns out that those can be made nicely by, those can be made nicely by adding borate reagents similar to the dicyclohexylborane or the 9-ppn reagent that we used. This catechol-borane will add across the carbon-carbon triple bond in the standard manner, giving a syn addition. Where the boron is attacked so that it ends up at the less substituted end, and the hydride is delivered to the more substituted end. To generate the alkylborane, which can be isolated, and hydrolysis aqueous acid cleaves the two boron oxygen bonds to generate catechol. And the alkylboronic acid. So it's relatively easy to access these alkylboronic acids with a wide variety of alkenes. Using chemistry that you're familiar with, the catechol-borane, because of the lone pairs on the oxygen, able to donate to the boron to stabilize it, are less reactive than ordinary alkylboranes, which prevents you from adding two across the triple bond. It adds to the triple bond, but it doesn't add to the double bond. The mechanism of palladium catalyzed cross-coupling reactions has some similarities to the mechanism of the Heck reaction. It starts with the same divalent palladium 0 compound, this triphenylphosphine palladium 0 in this case. Which is either generated in situ from palladium acetate and triphenylphosphine, or from tetrakis triphenylphosphine palladium 0 through the loss of 2 of the 4 ligands. And like the other reactions, it does an oxidative bond insertion. Into the alkenyl, or in this case, phenyl iodide. And we now have palladium in +2 oxidation state. There's probably a cis-trans isomerization at some point with these two sterically bulky ligands preferred to be in trans orientation. And then there's a transmetallation reaction where another organometallic results from the reaction of copper iodide with the alkyne. The alkyne binds to the copper to form a complex. And then in the presence of your tertiary amine, reacts to form a copper, an alkynyl copper compound. And the trialkyl ammonium iodide. There's now a transmetallation reaction where the alkynyl group adds to the palladium and the iodide adds to the copper. So the net result will be to switch metals so that the alkynyl group is now attached here, and the iodide goes with the copper, which allows the copper iodide, the cuprous iodide, to go back in to the cycle and add another alkyne. The rate determining step in this mechanism is actually thought to be the isomerization from this trans complex to the cis complex. And then there is a reductive elimination pathway where palladium 2 is reduced back down to palladium 0. And the carbon-carbon bond is formed. Forming our product. So similar to the Heck reaction, oxidative bond insertion, but now instead of an alkene directly complexing to the palladium and then having that alkyl or alkenyl migration, we have a transmetallation where another organometallic delivers its alkyl group to displace the halide, iodide or bromide that's attached to the palladium. Now we've got our two, in this case our aryl group and our alkynyl group both attached to palladium. There's an isomerization to put them cis to each other, and then they can do this bond migration. This carbon-palladium bond becomes a carbon-carbon bond and returns the pair of electrons to palladium to make it palladium 0, and then that palladium 0 compound goes back into the cycle. So we've actually got two cycles. We've got a palladium cycle and we've got a copper cycle, or in the case of the Spilling reaction, a tin cycle, or in the case of the Suzuki reaction, you've got a boron cycle going on the other end.